The Vanadium Redox Battery, VRB, also known as the Vanadium Flow Battery, VFB, or Vanadium Redox Flow Battery, VRFB, is a type of rechargeable flow battery. It employs vanadium ions as charge carriers. The battery uses vanadium's ability to exist in a solution in 4 different oxidation states to make a battery with a single electroactive element instead of 2. For several reasons, including their relative bulkiness, vanadium batteries are typically used for grid energy storage, i.e., attached to power plants/electrical grids. History. Pissoort mentioned the possibility of VRFBs in the 1930s. NASA researchers and Pellegri and Spaziante followed suit in the 1970s, but neither was successful. Skyllas-Kazacos presented the first successful demonstration of an all-vanadium redox flow battery employing dissolved vanadium in a solution of sulfuric acid in the 1980s. Her design used sulfuric acid electrolytes, and was patented by the University of New South Wales in Australia in 1986. One of the important breakthroughs achieved by Skyllas-Kazacos and co-workers was the development of a number of processes to produce vanadium electrolytes of over 1.5 m concentration using the lower cost, but insoluble vanadium pentoxide as starting material. These processes involved chemical and electrochemical dissolution and were patented by the University of NSW in 1989. During the 1990s, the UNSW group conducted extensive research on membrane selection, graphite felt activation, conducting plastic bipolar electrode fabrication, electrolyte characterization and optimization, as well as modeling and simulation. Several 1 to 5 kilowatts VRFB prototype batteries were assembled and field tested in a solar house in Thailand and in an electric golf cart at UNSW. The UNSW All-Vanadium Redox Flow Battery patents and technology were licensed to Mitsubishi Chemical Corporation and Kashima Kita Electric Power Corporation in the mid-1990s and subsequently acquired by Sumitomo Electric Industries, where extensive field testing was conducted in a wide range of applications in the late 1990s and early 2000s. In order to extend the operating temperature range of the battery and prevent precipitation of vanadium in the electrolyte at temperatures above 40 C in the case of VB, or below 10 C in case of the negative half-cell solution, Skyllas-Kazacos and co-workers tested hundreds of organic and inorganic additives as potential precipitation inhibitors. They discovered that inorganic phosphate and ammonium compounds were effective in inhibiting precipitation of 2M vanadium solutions in both the negative and positive half-cell at temperatures of 5 and 45 C respectively, and ammonium phosphate was selected as the most effective stabilizing agent. Ammonium and phosphate additives were used to prepare and test a 3M vanadium electrolyte in a flow cell with excellent results. VRFB's main advantages over other types of battery. 1. No limit on energy capacity. 2. Can remain discharged indefinitely without damage. 3. Mixing electrolytes causes no permanent damage. 4. Single charge state across the electrolytes avoids capacity degradation. 5. Safe, non-flammable aqueous electrolyte. 6. No noise or emissions. 7. Battery modules can be added to meet demand. 8. Wide operating temperature range including passive cooling. 9. Long charge/discharge cycle lives, 15,000 to 20,000 cycles and 10 to 20 years. 10. Low levelized cost, a few tens of cents, approaching the 2016 5 cents target stated by the U.S. Department of Energy and the European Commission Strategic Energy Technology Plan 5 euro cents target. Disadvantages. VRFB's main disadvantages compared to other types of battery. 1. High and volatile prices of vanadium minerals, i.e. the cost of VRFB energy. 2. Relatively poor round-trip efficiency, compared to lithium-ion batteries. 3. Heavy weight of aqueous electrolyte. 4. Relatively poor energy-to-volume ratio compared to standard storage batteries. 5. Having moving parts in the pumps that produce the flow of electrolyte solution. 6. Toxicity of vanadium, V, compounds. Materials. A vanadium redox battery consists of an assembly of power cells in which two electrolytes are separated by a proton exchange membrane. The electrodes in a VRB cell are carbon-based. The most common types are carbon felt, carbon paper, carbon cloth, graphite felt, and carbon nanotubes. 18, 19, 20. Both electrolytes are vanadium-based. The electrolyte in the positive half cells contains VO2+ and VO2+ ions, while the electrolyte in the negative half cells consists of V3+ and V2+ ions. The electrolytes can be prepared by several processes, including electrolytically dissolving vanadium pentoxide, V2O5, in sulfuric acid, H2SO4. The solution is strongly acidic in use. The most common membrane material is perfluorinated sulfonic acid, PFSA or naphthalene. However, vanadium ions can penetrate a PFSA membrane and destabilize the cell. A 2021 study found that penetration is reduced with hybrid sheets made by growing tungsten trioxide nanoparticles on the surface of single-layered graphene oxide sheets. These hybrid sheets are then embedded into a sandwich-structured PFSA membrane reinforced with polytetrafluoroethylene, Teflon. The nanoparticles also promote proton transport, offering high coulombic efficiency and energy efficiency of more than 98.1% and 88.9%, respectively. Specific energy and energy density. VRBs achieve a specific energy of about 20 Wh/kg, 72 kJ/kg, of electrolyte. Precipitation inhibitors can increase the density to about 35 Wh/kg, 126 kJ/kg, with higher densities possible by controlling the electrolyte temperature. The specific energy is low compared to other rechargeable battery types. For example, lead acid, 30 to 40 Wh/kg, 108 to 144 kJ/kg, and lithium ion, 80 to 200 Wh/kg, 288 to 720 kJ/kg.